Alright, silly people, here's the situation. We're going to be looking at the scattering states for the step function potential, which is given by this equation here, and then also I drew the little graph of it there, just so we're all on the same page. Um, and we specifically are going to calculate a bunch of reflection and transmission coefficients for this. Um, so I've labeled the regions 1 and 2, like always, and right off the bat, I'll tell you that the wave function for the first region um, is going to be the same as it always is when there's zero potential. It's just a e to the I kx plus b e to the minus I kx, right? Um, where k is defined, of course, as being roots 2 me over h bar. Okay. Um, the next thing we need to do is we need to write the Schrodinger equation in the second region. Uh, h bar squared over 2m del squared psi 2 del x squared plus v naught psi 2 equals e psi 2. And it's not like we haven't seen this equation before, so it won't terrify you if I put it like this. And then this is going to be minus 2m over h bar squared e minus v naught psi 2. And what happens next is dependent on the case that you're looking at. So I'm going to do the case where um, e is less than v naught first, going in the order of the problem. Um, in that case, we can define a L that is going to be just the square root of 2m v naught minus e, kind of like what we did in the last video, um, over h bar. And since e is less than v naught, L is positive and real. And we can write the Schrodinger equation now just like this. L squared psi 2, which has a solution of psi 2 equals, I'm going to say that this is called uh, c e to the lx plus d e to the minus lx. But since we have the boundary condition that psi at infinity better be equal to 0, we can actually get rid of c so that we don't blow up at infinity. So we just keep the d term. And to get the reflection coefficient from this, all we have to do is we have to use a couple boundary conditions. First of all, that the wave function will be continuous at the boundary, which is at 0 this time. So we have a plus b equals c. There's no c anymore, so just d. That's cool. We can also look at the condition del psi 1, or I'll write 2 on this side because I've already started 2, evaluated at 0 equals del psi 1 del x evaluated at 0, which is just giving minus L d equals IKA minus IKB. Whoops. And we can plug in what we just got for d from the last boundary condition, so we can say this, and then we can solve it so that the a stuff is on the right side. So 2, or actually a times k plus L, it's ik plus L, And on the left-hand side, we'll put all the b stuff. So it's going to be b times ik minus l. Right. Pretty cool stuff that. If you take the square modulus of both sides, then you just get the same term for both, because it's k squared plus l squared for both of these. So those terms cancel out, and we get that b squared over a squared, which, by the way, is the reflection coefficient, is just 1. Now, does that mean that 100% of the wave function is reflected against the barrier? Not really, because the wave function exists on the other side of the barrier. There is a side, too, that's non-zero. What's happening, to my understanding, is that when you actually measure a particle that has this wave function in this potential, that you're never going to find the particle on the other side of the potential. You're always going to find it back on the other side, just because the wave function exists in quantum mechanics. That doesn't mean that when you actually observe the thing, that it's not going to act like a classical wall that is bouncing back everything. So that is a perfectly sensible answer, I think. But then we have to look at the case of E greater than V naught. So for E greater than V naught, just looking back at our differential equation here, it is now more useful to define an L, which is equal to root 2m E minus V naught, so that we can have a constant that is real and positive. But then we write the differential equation now like h bar, nope, there's no h bar squared anymore. There's just del squared psi 2 del x squared equals minus L squared psi 2, which has the familiar solution of f e to the minus I L x, given that we're assuming scattering from the left. If we weren't, then there'd be another constant there, but we're not. And that actually is plus ILX. Yes, assuming that we're scattering from the left. So that's psi 2. We can get the reflection coefficient for this guy, again, by doing boundary conditions. So we have the first condition again, that they're continuous at 0. It's not A. So psi 2 at 0. So we have A plus B equals F. Pretty cool boundary condition there. Then we have that the wave function is smoothly varying at the boundary. So this guy again. And so that's looking like AKA or IKA times e to the IKA. But it's not e to the IKA because now it's just 0. So IK capital A minus IKB equals just ILF solid. We can cancel out the i's, so we have less imaginary stuff to work with, and then we'll put in what we just got for F from the first boundary condition, so we have that sort of thing. And now, putting all the stuff which depends on A on the left side, we have K minus L, and all the stuff which depends on B on the right side, so we have K plus L. Yeah. Um, and now we, when we take the square modulus of both sides, we have this sort of thing going on, where we have mod b squared k plus l squared, and so b squared over mod a squared uh, is the reflection coefficient, which is k minus l squared over k plus l squared. And there's a pretty funky way to deal with that, because if you try and plug k and l in right now, you're going to have a bad time. The way to do it is you multiply the equation by 1, and by that I mean multiply by k minus l squared over k minus l squared. And so on the top side, we just have k minus l to the fourth, which is a little bit weird, but it's okay. And then on the bottom, we can move the parentheses terms into the same square. So we have k plus l times k minus l, and all of it is squared. Cool. Um, the interesting thing about that is now we can write it as just, and I'm going to switch back to regular parentheses, because that's just going to be k squared minus l squared, all squared. And now it's worth plugging in the definitions of k and l. So this is going to now be a little bit gross. So k was root 2me over h bar, and then l was root 2me minus v naught all over h bar, and we get to raise all of that to the fourth, and then k squared was 2me over h bar squared, and l squared was 2me minus v naught over h bar squared, and it's all squared. Right. Cool thing about this is that, well, I guess it's not that cool. I mean, let's be honest with ourselves. This is pretty nerdy. We'll just pull out the root 2m over h bar thing to the fourth, and then inside here, we'll just have root e minus v naught, and then that's raised to the fourth, and similarly on the bottom, we'll have a 2m over h bar squared, all squared. Now this term is the exact same as this term up here, just square this and you get the same thing, so we'll cancel them out right now. But then we still have this e minus e plus v naught in the square. And those e's cancel out, so that's funny. So all in all, we will have the root e minus root e minus v naught, and it's all squared. And then and that's not all squared, it's all to the fourth, because this problem had to be fancy. Yeah, all to the fourth. And then just v naught squared on the bottom. And you can leave it like that for the reflection coefficient. It's a convenient form for it. Because the next thing we're going to do is we're going to calculate the transmission coefficient. And it's a weird one because the transmission coefficient is not just going to be f squared over a squared like usual, because there isn't a drop-off of the potential on the right-hand side. So we have to do a more fundamental equation for the transmission coefficient, which is just that it's the probability current in whatever region you're scattering or tunneling into, divided by the probability current of whatever's on the other side. Um, right? Um, and then Griffiths alludes to problem 2.18 for a reason in this part of the problem. So do go watch that video, and you can. It's the same sort of calculation, and you find that J2 will just be given the wave function that it is. It's just mod squared f times h bar k, or h bar l, because there's an l in the exponential for this one, over m. And similarly, J1, it's h bar k a squared over m. Same sort of thing. And so the transmission coefficient is just this divided by this. So it's t is just L over K mod F squared over mod A squared. And we can plug in what we have for L and K. So we have the square root 2me minus v naught over h bar squared over the square root 2me over h bar squared, and then multiplied by f squared over a squared. The h bar squared terms will get canceled out, so we just have root e minus v naught up top, and then v naught, no, it's not v naught, it's e on the bottom. And that looks like what Griffiths was getting for that part as well. So that's pretty convenient, pretty nice. At this point, I feel like it's a weird time, but Griffiths asks, oh, well then what is the transmission coefficient for the other case? Which is, again, I'm going to do it in gray, for E is less than V naught. What is T? And since we found that the reflection coefficient is 1, and we have this fundamental equation, which is based on normalization, that T plus R equals 1, we can surmise that T equals 0 for E less than V naught. Which again doesn't mean that the wave function doesn't exist on the other side of the barrier. It just means that when you observe it, you're never going to observe the particle on the other side of the barrier, because it's, yeah, no probability of transmission. So that's funny, but now we actually have to do this calculation of the transmission coefficient for the other case. So we have to get f squared over a squared somehow. So let's go back to the equations which we derived from the boundary conditions for this case. So the first boundary condition entered in the equation a plus b equals f. Let's use this to solve for b instead now. So we have b equals f minus a. And then the other boundary condition that we had was Ka minus Kb equals just LF, right? And then we can plug in what we just got for B now. So we have minus Kf plus Ka equals LF, and then we'll put all the A stuff on this side and put the L stuff on the other side, so F L plus K. Um, that's fine. And then if we take the square modulus of both sides, we get 4K squared mod A squared equals mod F squared L plus K squared, right? So solving that for F squared over A squared, we have mod F squared over mod A squared equals 4K squared over K plus L squared. Okay, that's pretty epic. So now let's plug this into our form for the transmission coefficient, which is now looking like it's probably worth putting it back into this form which we derived first of all. So L over K, and now this is 4K squared over K plus L squared. And so we do get a little bit of cancellations of K's, but not that much, before we have to start messing with this again. And this time, again, we're going to multiply the top and bottom by K minus L squared. Same trick as before. So this is K squared minus L squared, all squared down here. But now expand what K and L are in each thing. So this is going to be another big old fraction. So we've got 4, and then K was root 2m, just E, and that's going to be over h bar. And then we have L, which is 2m E minus V naught, all over h bar. And then in the square, we have same things. This is over h bar, and then this is 2m E minus V naught, all over h bar and squared. On the bottom side, K squared was just 2m E over h bar squared, and then L squared is 2m E minus V naught over h bar squared, and it's all squared. Cool stuff there. From here, on the top side, we'll factor out a total 2m over h bar to the fourth, much like before. But now we just have 4 root E minus V naught times root E minus root E minus V naught squared, and then it's going to be over 2m over h bar squared, all squared, and this is going to be multiplied by E minus E plus V naught, again, all squared, and so these E's cancel out, these terms cancel out, and we're left with like the simplest form that we can get, but it's still pretty gross looking. 4 root E times root E minus V naught, and let's group those into the same radical for prettiness purposes. E minus V naught, in parentheses there. And then this is root E minus root E minus V naught. And then that thing gets squared. And then we just have V naught squared on the bottom. Cool. Last thing Griffiths has us do is check this equation that t plus r is equal to 1. uh, which it has to for normalization purposes. So we have t now, so let's write that out. Um, but actually, let's not write it out. Let's just leave it in a simpler form that we derived earlier. Uh, yeah, let's just do this form right here. So uh, 4kl over l plus k all squared, right? And then the reflection coefficient, we did it a while ago. It was k minus l squared over l plus k squared. So we've got the same denominator already. So let's just expand this polynomial here. So we have k squared minus 2kl plus l squared. That's all over l plus k squared. And then we can simplify that a bit just by doing the addition terms. So it's k squared plus 2kl plus l squared, l plus k squared. And then we can factor the top line. So we have k squared plus l, and it's not squared inside, it's squared on the outside. Oh my goodness. Yeah, but it is just k plus l squared on the top, and then this is k plus l squared on the bottom, so they cancel out, so you get 1 for the t plus r. So we're all good with our answers there.